So, hi Simon, welcome on stage.
Hello, can you hear me?
I can hear you very well.
That's
So,
good.
yeah, delighted
Excellent.
to have you.
Right, I will try and use the technology. Excellent. Well, thanks very much for the introduction, and thank you to Lynn for the introduction to our part on OTFT. So today I'm going to talk about our organic thin film transistor technology and describe how we're moving this from a lab-based activity into something which is becoming more of a fabrication facility for making devices. So as you might imagine, we're a materials company. We're based in Manchester in the UK, roughly central to the UK. And within this building here on floor 8, we do the materials R&D, synthetic procedures, formulation, scale up and development, and some device R&D. The rest of the device R&D and process development is done at the Centre for Process Innovation, which is a kind of UK national lab for printed and plastic electronics based in Sedgefield near Durham in the northeast. So this contains a lot of process equipment that allows us to do photolithography, sputtering, wet etching, dry etching, a lot of the common things that you would do in a display fab line. Obviously, a lot of the display industry is in Asia. So for flexible base display developments, we are linked with organizations, including Linksil, that Lynn introduced earlier. And we work a lot in Taiwan with the Taiwanese display industry. And there we have a field applications engineering team. And we've recently established a collaboration with ITRI in order to put our materials onto their pilot line at Gen 2.5 scale. So this is for doing pilot scale developments of products that customers in Taiwan would like to produce at a high quality using our materials. So the organic thin film transistor is not radically different from other thin film transistor devices. It has electrodes, which are generally made by sputtering and patterned using photolithography. And then we provide all of the organic materials that go within the organic TFT, including the semiconductor, gate insulator. The SRL is called a sputter resistant layer, and that allows it to go through a conventional sputtering process for the gate. And then we can provide passivation materials and base layer materials, which are kind of inert dielectric polymers, which isolate one layer from another. So we provide all the materials in a formulated clean room package compatible formulation from sizes from 100 milliliters up to 3.3 liters. All the materials are developed with a high performance, so we have charge mobilities around about 2.5 to 3 centimeters square per volt second at short channel devices. And short channel is typically display industry short channel of 3 or 4 microns. They have high on-off ratio. This is limited by the test system, so the actual on-off ratio is potentially even higher than 10 to the 8. They are low temperature processable materials, and I'll go into more into detail about the consequences of that for device applications. And the materials are designed to go on existing amorphous silicon lines. So it's designed to be a drop-in for today's fabrication lines with minimal reinvestments. So compared to other thin film transistor technologies, our temperature of processing can be as low as 80 degrees C, typically below 150 degrees C, but we've demonstrated down to 80 degrees C as a proof of concept. Most of the TFT technologies require processing in excess of 300 degrees, even towards 400 degrees. And that is mainly for the PECVD process for putting down the silicon nitride dielectrics, which tend to become worse if you lower the temperature. So hence they're not very plastic compatible, and you have to process the backplane before you're doing the rest of the device. So this is the main differentiator in that we can use this to our advantage, and people can use it for making devices on novel types of plastic substrates or making them devices in novel ways. The process for fabrication uses photolithography via masks or direct photolithography. We make a dual gate device, which includes a back gate and a front gate. We've got various passivation layers and source drain metal patterning. And then we can take this 5-mass process and develop lots of different types of devices by varying the latter